Everybody had a good weekend? Talking about a little bit, sounds good. So some announcements, and then we'll be starting my favorite topic, the one I've been excited for this whole semester, about talking about cool grammar stuff, and not grammar stuff like how to use commas, but more computer sciencey grammar stuff. So announcements quickly. So there's been 6 of the homeworks submitted. Most of them were full credit so far. If they weren't full credit, then I left a note about why, and you can resubmit for full credit still. On Tuesday, I will start deducting late points for late submissions at that point. So get your submissions in by Tuesday. Any questions about the homework at all? Everyone enjoyed fighting against RASP? One of the cool things that we'll be talking about with this grammar section is like how to implement your own programming languages, kind of like RASP. And as part of that, and there were a bunch of issues, and people just sort of informally talking with me about like how do you even like get started with there's undocumented features in RASP and understand what's going on. Eventually, for these sorts of languages, you just have to dig into the code and see what it looks like. And it's a very overwhelming task, but with a good understanding of this grammar stuff, it'll be much more approachable to dig into the RASP code or other programming languages like RASP, and you'll at least have a fighting chance to figure out what's going on with things. Okay, so that's it about the homework. Next steps on the projects. So most of you have finalized your project stuff, but if you still haven't done that, please do that still. In 2 weeks, so on November 4th, I'll ask you all to submit to me your grading rubric, what you think should be the correct grading rubric for your project. And so I'm not going to give you a whole lot of details about how to format that or what to do, because you should do that whatever makes sense to you for your project. But the specific things you'll need are some list of tasks about what you will accomplish and what percentage of your final grade each one of those tasks is worth. And so when we sit down, and I have decided that we'll do the presentations about your projects one-on-one. I think that'll be easiest for everybody. It'll make scheduling easier and allow me to give you all better feedback about things. But when we sit down and do that one-on-one, we'll have this checklist of tasks and just go through them, and I will check them all off, hopefully, and say that you got 100% on your final project. But you will have to decide here exactly what those things are for your specific case that need to happen. And so again, you have 2 weeks to do that. I will either approve it or suggest revisions to your rubric there. And the way that I think about this sort of assignment is that you're like writing a contract with me about what exactly it is that you're going to be doing. And we might negotiate that contract a little bit, but once it's approved, all you have to do is complete that contract for your project, and you'll get your good grade. Any questions about this? Yes. So it'll be over finals week. Just I'll have a Google Docs or something to schedule things, but you'll have a flexibility about scheduling that, so you can, if you need more time based on you have a lot of other stuff going on, you can schedule it later in the finals week, or if you want to get done and leave for summer early, you can schedule it earlier. Yeah. Good question. Any other questions about project stuff? Yes.
We should be having a page kind of tracking our progress, and would we also want to have like this rubric on GitHub? Or I was curious how you like publish your research or sort of like planning on GitHub when you're doing a project like this.
Yeah, it's a good question. So one of the requirements for your project, there is again this in the class repo, there's a final project folder here that lists some, again, not very detailed, but some requirements for the project. One of those requirements is a GitHub repo. That's your main thing about the project. And so I would recommend just creating that repo immediately, and every time you're working on the project, adding stuff, committing whatever you're doing to the repo. The point of Git and GitHub is that it's a tool that helps you track your own progress and helps you do various things. So you should take advantage of it, use it as you're going. Don't just wait till do everything without Git, and then the last day before it's due, put it into Git. The rubric here itself. I'm open to having you guys creating a rubric.markdown file or something in your GitHub repository, if that's convenient for you, or if it's an issue in your repository, whatever's convenient for you, basically, to do this. I don't know if that answered your question or not. Very vague answer on my part.
Yeah, I was just looking more for how are you supposed to maybe get that vision place where you outline your project plans besides just commenting certain things that you're going to do.
Yeah, let's see. So I do everything in text so that I can use it with Git, and yeah, so I would just have a text file of my notes that's in the project repository. I have probably close to around 1,000 repos on GitHub that have projects that I started, and that just has random text notes about things inside of it. And so that's how I would organize things, but you're not required to organize it that way. Good question. Other questions? Anything administrative in the class? Okay, the last, administrative note here is that you'll have somewhere between 2 and 4 homeworks on this grammar topic here. I have the first one posted. We'll go over the first one today, and then we'll see how many. It's not really about the amount of work, how many homeworks there'll be here, but just how I decide to split them up for you all to organize things. Okay, so our learning objectives, talking about grammar here, related specifically to LLMs, we're going to want to figure out how to what's called constrain the large language model output. So we saw a little bit about that with LMQL, but a little bit more generally, talking about constraints on the LLM output, like how do you make something be exactly JSON output, or exactly a CSV file, or things like that. Constraining your LLM to have some sort of particular output. We'll also be talking about how to design a programming language. Again, creating your own new language. So things like RASP or LMQL, they all have associated grammars for them. How do you define that? How do you use that to learn other people's languages? And we'll see examples like Python, SQL, JSON. They all have grammars associated with them. How do you read those grammars to better understand these languages? Or again, non-standard languages like RASP and LMQL. How do you read their grammars to understand those languages? Everything we're going to talk about, this will probably take definitely more than this week, maybe 2 weeks, maybe 3 weeks. But this is basically a speed run of 2 semesters of standard CS curriculum, highlighting the things that I think are the coolest, most important things, and often not even covered in classes like CS 81 and 132 here. Okay, so our first homework assignment, whisper.cpp. Anybody here used whisper.cpp? Heard of it? Heard of it? Okay, cool. People hands. We'll be using it to create a personal assistant application, and so due date here next Sunday. We're going to see so CFG here stands for context-free grammar. We'll see exactly what that means later on, but how you constrain your model output with these context-free grammars and how that will improve performance. And one of the big parts so for this assignment, the grammar part will be relatively easy, but this part down here could be, depending on your background, very new for you, how to use non-Python programs to accomplish things. So whisper.cpp, written in the combination of C and C++, and you'll have to navigate that a little bit in order to get the program working. Okay, some background here. I got a big timeline of things here that I want us to talk about. So in 2022, September 22, OpenAI releases this model called Whisper. It is, so SOTA stands for state of the art. I see this acronym thrown around a lot in machine learning, state of the art. And then ASR, automatic speech recognition. So basically, if you think YouTube, how it subtitles all of videos on YouTube these days, it's using automatic speech recognition. YouTube uses Google's own internal thing, not Whisper, I think just for internal political reasons, but Whisper is the state of the art, the best one that exists right now. And Whisper, one of the things that was very surprising about it when it first came out was that it basically supports the vast majority of languages that have like actual meaningful populations of speakers. So like 99% of people in the world who their native languages are supported by Whisper. Their official announcement here, GitHub repo here, you can take a look at those if you're interested. One thing I find interesting here is that this is sort of the last major release from OpenAI that is where they release their models publicly, non-commercially. So 2022, September, this OpenAI was still a nonprofit at this point. They are no longer a nonprofit, they're now commercial. And I don't expect further releases like this. I was a little bit surprised. 3 weeks ago, OpenAI, at this point, they were already a commercial enterprise, not a nonprofit, but OpenAI did release an update to Whisper called Whisper v3 Turbo. It's much faster than the previous Whisper models and still pretty accurate. And so I was surprised that they released this publicly, but it's also not on their, they have no official announcement about it. It's just like an issue on their Whisper models GitHub repo where they talk about this. And my sense is that the reason they did this is because they had a lot of pressure from other developers were doing improvements to the Whisper system. And so they wanted sort of control about what those improved systems looked like. And so this is their version of those improved things. Okay, so whisper.cpp is an open source alternative implementation to this GitHub repo right here. It still uses the same model internally, but it's a different implementation of the actual code, implemented in C, C++, designed for inference on device instead of in the cloud. So handful of advantages for that. One of them is privacy. That's the most obvious thing, that if you're using whisper.cpp, you don't have to send your information over to OpenAI. And so doctors, for example, can use whisper.cpp to transcribe medical notes without like HIPAA violations. But it actually turns out to be much, much faster for things like this grammar stuff that we'll talk about, because you'll avoid a lot of overhead involved with using the cloud. Whisper.cpp also optimized for Apple hardware, laptops and iPhones, and CPU inference. So it's surprisingly fast on like very low-end devices. I'm going to do an example here in a little bit on this laptop, and this laptop is now a 12-year-old laptop, pushing 13-year-old, and it still runs reasonably well, whisper.cpp. The more famous version of this code base is llama.cpp. They're both made by the same author. Llama.cpp, originally designed for Meta's Llama models, now supports most LLMs, made by, I put a nobody in quotes here, scare quotes, because he's not a nobody anymore, but a random dude from Bulgaria, who's now become one of the most influential people in the LLM scene here. And he's got a cool story here if you're interested in reading that. There's a famous picture about open source projects, just like there's often random open source projects that are supporting like huge infrastructure on things. But a lot of businesses now depend on llama.cpp or whisper.cpp, and it's just this random guy from Bulgaria who's maintaining all this. Unpaid. Okay, so starting to talk about a little bit about this context-free grammar stuff. We'll get into details about what it means to have, like, what exactly is a context-free grammar, what can you do with it in a little bit. But I just want to do a little bit more timeline stuff to see how fast all this stuff has been moving. So llama.cpp is, I believe, the first LLM library that supports using these context-free grammars to restrict your output, to constrain models in some way. There were a handful of people using regular expressions before this, and there's probably like 5 or 6 libraries, so I didn't list them all here. But they go back no earlier than 2022. And we'll see in a little bit, by the end of today here probably, that context-free grammar is much, much more powerful than regular expressions. An example of something you can do with context-free grammars is JSON support. You can do that with context-free grammars, but you cannot do that with regular expressions. So Meta, Facebook releases February 2023 their Llama model weights, llama.cpp, their first commit. So one of the fun reasons about why using GitHub is you can actually track the history of these like famous important projects, see exactly what their first commits are on things. So here, first commit on March 10th right here. And so that's when llama.cpp came about, 3 weeks after Meta releases this program right here. It gets regular expression support exactly 2 months later. And then this context-free grammar support happens 4 months after Llama was released. At this point right here, the llama.cpp was state-of-the-art for very, very many tasks, not tasks that have particular benchmarks on them, but any task that involved any sort of structured output. Llama with these old Llama models, llama.cpp with these old Llama models was handily beating OpenAI on those tasks. So in particular, anything that required like very strict JSON compliance, you could do that with, at this point, exactly 1 year ago almost, with llama.cpp, couldn't do that with OpenAI. OpenAI, in response to this, they add their JSON mode support in November last year. And this is sort of just a special case of this context-free grammar stuff, this JSON mode support. They still have no native support for non-JSON languages. There are some other external projects, again, like LMQL that provide some support. But because if you're using OpenAI, you're using the stuff in the cloud, there's going to be a lot of back and forth between your computer and the cloud. It's all going to be relatively slow. LMQL, as an aside, does offer llama.cpp as a possible backend that you can use. So this is not like an OpenAI specific technology. It would work with llama.cpp as well. And then a note here. So G. Jeranov, that's the Bulgarian guy's GitHub handle. He didn't implement actually any of these features. He didn't implement the regular expression support or the context-free grammar support. But he still basically gets all the credit for it because he sort of fostered this environment where lots of people wanted to contribute these features to llama.cpp. And at this point, the vast majority of the code base for llama.cpp not written by G. Jeranov, but he still is like the gatekeeper of what actually gets in and what doesn't. Okay, so again, 2023 0608 llama.cpp gets this support for context-free grammars. What is this? September, October. That's not October, is it? January, March, April, May, June, July, August, yes. August, whisper.cpp gets this context-free grammar support. Again, the difference between whisper.cpp is whisper.cpp taking audio, outputting text, llama.cpp taking text as input, outputting text. And at this point, as far as I know, this is the only system that supports context-free grammars in any way related to audio. OpenAI doesn't support it in any way. Things like LMQL, even when you're bridging with OpenAI, they're focused only on the text aspect of inputs, text models, not on audio models. And so it's been almost a year now, over a year now, since this was added to whisper.cpp, and it's still the like really the only thing that supports this. Okay, so why should we care? That's our timeline. I've made some claims about like this is cool, and it's whisper.cpp, llama.cpp, state of the art in many ways. But like, why should we care? What are some of the things that we can do here with this technology that we can't do with other things? And I think chess provides a really cool example. I'm going to go to this link right here, which I already have opened here. And this is a link of, well, so one of the nice things about like whisper.cpp, llama.cpp, because they're written in C, C++, it's easy to transfer them over to web pages and have them run on the web. You can't do that with Python, but you can do that with C, C++. And so this is a little chess app right here that is written using whisper.cpp to have a text-to-speech system. And chess is a really hard thing for text-to-speech because there's a lot of ambiguous words in chess. And so I'm going to open up here a real quick window so I can type things so we can see what that ambiguous words are. But if I were to say something like, talk about a knight, the words knight and knight like this, in English, they're pronounced the same way, the vast majority of dialects. But if we're in the context of chess, we're probably talking about this kind of knight. But if we're in the context of any other situation in real life, we're probably talking about this kind of knight. And so one of the things that whisper.cpp is going to do is by itself, if it just hears us say the word knight without any context, it'll use this knight. How do you spell knight? Why is that like that? We'll do it. I don't know. That is how you spell knight, isn't it? Yeah. Got off track there. If you're just talking to whisper.cpp and it's translating things into text for you, then by default it'll want to say this kind of knight when it hears the word knight, but we're going to be able to enforce it to say this kind of knight instead. Another way this comes up in text or in chess is so these pawn pieces up here. Pawn is a very rare word in English. Rare word, but it sounds like a lot of more common words like pond or paw on a dog or bond, like the bonds in economic literature. And in context, if somebody were just to say the word pawn without a chessboard in front of here, I would probably in my head hear one of these other words and not the word pawn. And so the whisper.cpp, these models, these text-to-speech models or speech-to-text models will not pick up these sorts of very rare words very easily. But we can constrain our model to let it know that it's working in a chess environment so that it has to be this word and cannot be any of these other words. One last example here is the phrase E4. E4, very common phrase inside of chess. In chess, so we have an 8x8 grid here. Letters denote the different columns. You can see the letters down here, A, B, C, D, E, F, G, H. And numbers denote the rows, 1, 2, 3, 4, 5, 6, 7, 8. E4 refers to this square right here, and it's one of the most important squares in chess. But it sounds a whole lot like the English word before. And so a standard speech to text thing, if you say the words E4, it will probably output something like B4 because this is much more common in ordinary English than this. But in the chess world, E4 much more common than B4. So our context-free grammars are going to allow us make a system that encourages outputs that are geared towards our domain, like chess here, knight, or pawn, or e4. Okay, in order to do this, maybe one other side note too. So the models that I'm going to be using here are all very small models. So tiny.in model right here, 42 megabytes in size. The standard large Whisper model, multiple gigabytes in size. So on a web environment where we care about bandwidth, it's nice to have users download only smaller models. It's also the case that these smaller models much faster to do inference with. So you can get much more real-time results with them on low-end hardware, whereas the large models much slower. The downside of these smaller models is that they are much less accurate. But again, with this context-free grammar stuff, we'll be able to apply these constraints, getting more accuracy from these models. So with this setup right here, there's a handful of these examples. They all have at the top a set of models that you can select from. I press select right here. It's now downloaded that model for me and loaded it. I've just given my browser here permission to use the audio on my computer. And then down here is some like debugging output. This is all the output internal to Whisper, so we can see what's going on. And I'm gonna just say some chess moves into a microphone over here in a second, and it'll move the board for us. And put on my microphone, and in order to register that I'm going to be talking, I'll press the hold button right here, press it and hold it. E4. Takes about 10 seconds on my computer to have it register. And E4 should hopefully take this pawn right here and move it up there. Yep, there it goes. So E4. It's the standard chess move for this pawn up here. The output right here, this is all of the context-free grammar stuff. We'll talk about that in a little bit here, but the hopefully the motivation here is at least somewhat obvious, that I'm just saying E4 by itself without any constraints, not obvious exactly what the corresponding output should be. But once we've applied these constraints, forcing it to be like chess moves, that is the output, then the only possible chess move that makes sense is moving this pawn up here to E4. Any questions about that? Yeah, easier.
How good is it at registering? Does it register like most of the time?
So in the context of chess here, it's like basically perfect. I guess my English accent is probably pretty standard for the what's been trained on in the Whisper model. So maybe somebody who's like a non-native English speaker might have more trouble here. But there's a very like small set of possible options about what the output space is. And so my sense is that like even a very like somebody with a very thick accent could play chess like this. So these models support basically every language that you've heard of. So even ancient Greek and Latin are both supported. So fairly rare languages supported by Whisper right here. Yeah.
So if you said like A quadrant, would it do the same thing?
Sure, I'll try an example here in Spanish. So I'll go, we'll do a cuatro, moving this pawn up to here.
Black's turn.
It's black's turn. So we'll do, so here's a particular hard example. So common thing for this pawn here to move down here to E5 afterwards. I'll say A5. A is a particularly hard val here to disambiguate because it's very likely to think of that as the English A and go the pawn down over here. A5. My guess for two reasons about why it's not going to get the right move going here to here is that the actual model that's loaded up here is an English specific one. They have a multilingual one that's equally this small size, but this one is English specific. Yeah, so it says failed right here, that it didn't even register that was a valid move because I said cinco instead of 5, and it doesn't know that cinco in English should correspond to the number 5. Yeah, so one of the nice things though about systems like this is that if it's not able to determine what the correct output should be, if it's not able to get it into this format over here like this, it doesn't like just make something up. It'll actually tell you that it failed. It can't do that. It doesn't satisfy these grammar rules down here.
Are those all the grammar rules that are being used?
This is the entirety of the grammar for the chess language here, what's allowed to be said. So we'll...
Well, where are the chess piece of loop rules? Like how did it know that E4 meant that it should be moved from E2? Anywhere else?
Yeah, so this is a good question here. So let's take a look at the output down here a little bit. When I said E4, the output of the whisper model was literally just the letters E4, because that is the chess command, E4, that moves the pawn from here to here. And then it took the output of that command, the output of whisper, and passed it into the chess engine that does the rendering up here and determining like what are valid moves and not valid moves. So the whisper model itself only giving us like the commands to this next language, this chess language, and those chess language commands getting passed to this chess program to do its thing. But this right here, this is the entirety of the grammar for the chess language. We'll break this down here in a little bit and see what it means. But it's fairly straightforward, something that with some practice would just be like a minute or two to write out. All good questions so far. Any other questions? Okay, so for your actual homework here, this is all background here on the homework. Maybe one last background thing. This llama.cpp and whisper.cpp, they do have Python bindings. They actually have like 20 or 30 different Python bindings, but basically nobody uses them because the project's moving so fast that the bindings are always out of date and they don't support any of the interesting features about these systems. So for example, I don't think there are any Python bindings that support this context-free grammar stuff. And so if you do want to use these like interesting features about llama.cpp or whisper.cpp, you basically have to use the C++ version from scratch. Okay, your actual tasks here. So you're going to clone the whisper.cpp repo onto your computer. And then one of the commands in whisper.cpp is appropriately called command. There are instructions at this link right here on how to build this command and what it does. The instructions for building it down here like this. A lot of the documentation and examples for this repository is in the form of videos, so you can hear the corresponding audio about what's going on and see whatever G. Jaranov has typed into his terminal down here to make the incantations work. There's also in these README files a lot of links to GitHub issues. The issues and pull requests on this repository, these are like the standard ways of documenting things. Again, everything is moving so fast in this library that there is no time for people to create their own like standalone documentation page. It would just be immediately outdated. And so there's some expectation that you're able to navigate these issues and pull requests to see the details about exactly what was going on and why here. This command tool, what it actually does is it is a like a personal assistant tool. I have, let's see, I don't know if I have it open already, but there's another online example right here. And you can do something like, here's the online demo right there. So this demo has two of these models here. I'll do the tiny model again, and I'll put on my headline thing. If I press start, then allow, you can see down here, this is what it's expecting me to say to start registering commands. So, okay, Whisper, start listening for commands. And speech detected, processing, and I can say something like, turn on the lights. And I said a lot of things into the microphone, so it might not detect turn on the lights. But you can, there's a set of commands like that, like turn on the lights or turn off the lights, that it's designed to register. Those commands will not directly turn on the lights or turn off the lights, but they will be sent, or you could send them to a system that would control, say, the lights in your house. Yeah.
Wait, how does this distinct from, is this also using?
This is also using a context-free grammar. This is just a different context-free grammar that, instead of supporting the chess language, supports languages for like an assistant, an automation of your house. This link right here takes us to, so click this link right here, takes us to the context-free grammar for assistant. So these are the examples of things that you can say into this context-free grammar here. And the context-free grammar itself looks like this. So still relatively, and with after we talk about what's going on here, you should be able to understand that in detail. The computer is really lagging, so I'm going to stop this, pause that, so it's not eating up all of my CPU here. Actually, I'm going to close that tab. Yeah, so everything up to step 3 here is just getting your system up and running. Step 4 here is the more interesting thing. You're going to have to modify the grammar up here. And again, we'll talk about the details of how to write these grammars in a bit. But you're going to modify the grammar so that there'll be a new command over here, which the command will be kill all. And the options to that command will be humans or animals or life forms or robots. And so you'll be able to command your computer to kill all humans, and it will register your command, and hopefully not carry it out, but it will at least register the command. And then you'll upload just to Sakai, demonstrating that your system does that. I said right here, upload a video of you issuing your commands to Sakai, but if for whatever reason recording a video is awkward for you, just a screenshot or something like that is fine as well. So we haven't talked about yet how to write these grammars. We'll do that here in a little bit. But are there any bigger picture questions about this that are not how to write a grammar, or what's going on in the grammar? Question, Alex? No? Yeah, Max?
What other projects have like gamified, or what other gamified projects have you seen Whisper being used outside of chess?
So one thing that I was trying to do, and I'm still trying to do, is being able to play Nintendo over voice commands. And so the Whisper model itself is designed to process 30 seconds of speech at a time, which makes it a little bit awkward for these voice commands, because you never give commands in 30-second chunks. They're like 2 or 3-second chunks. So there's a lot of like optimization stuff that has to happen for like real-time systems. I haven't tried using yet OpenAI's new, more efficient Whisper v3 Turbo. I think this might fix some of the problems that I was having for like Nintendo voice commands. but I haven't had a chance to try that yet. I've seen there's a handful of like YouTube streamers trying to do this, or not YouTube, but Twitch, doing this with other sort of video games, but they're all like real-time games, and there's always it's like a very awkward system that they have set up. Chess is, not being real-time, a better like fit for the system. But yeah, it's sort of like a still very new thing, and still like a very niche part of the large language model ecosystem here, that lots of interesting things that could be done here that haven't been done yet. Yeah, good question. Any other questions so far? Okay. We're going to spend the rest of today talking about these context-free grammars and how to write them and how to do things with them, exploring their interesting things about them. I've put the information about that under this other homeworks section right here. And there are 4 example Python files that we'll be going over in class today. My recommended way of going through this is to follow along with these. So I have these 4 Python files loaded in the GitHub repo here, and I would recommend just like downloading these files either by cloning the repository or downloading them one by one and following along with the different things that I do, walking through them. You don't have to do that though, but that's what I would find as the most helpful thing. As you're getting that set up, so my terminal screen over here, I have 2 terminals opened they're both in the same project folder. And on the right-hand side over here, I'll open up my Python files, vim example star.py-p. This will open up all 4 of those in one single vim window for me. And then on the left-hand side, I'll actually be running some things, and I'll do just Python 3 like that, and I want no numbers over here. There's 2 libraries that these files use, the RE library and the Lark library. RE is built into Python. There's nothing to install for that. Lark is its own standalone thing. And so in order to get access to Lark, you need to do pip3 install Lark here. Lark is one of the easiest to use Python libraries for these context-free grammars. And so that's the main reason that we're using it. But it's also very, very powerful. Most of the things that you can do with most other like parsing libraries, libraries for grammars are also called parsing libraries. You can also do with Lark here. Your next homework assignments too will be specific to inside of Python using Lark, doing different things with Lark. So what we're going to be talking about right here will help you write the grammars for the whisper.cpp stuff, but it's more directly related to the next programming assignments. Let's see, before I get started with going through the material, any questions on what my setup is or where I'm at? Okay. So here, my first note up here is that a language is a subset of valid strings. So this is in particular a formal language, but in the CS or linguistics community, we often don't say a formal language and we just say a language. And the most common, simplest of these languages are the regular languages. And regular languages are defined by regular expressions. Standard example is the example of AB repeated an arbitrary number of times. And that's what this regular expression right here tells us. Regular expressions, not an explicit prerequisite for the course here, but my hope is that most of you have been somehow exposed to them a little bit. But if not, there's very little stuff that we'll do with regular expressions here. So that's okay. This regular expression here, what it's telling me is that this up caret right here, this is the beginning of a string. Up caret, beginning of the line or string. The $sign, end of line or string. And in the middle here, inside of these parentheses, is the letters AB. And this plus right here says the stuff to the left of it. All of this stuff has to appear at least once, but it could appear more than once. So it could be AB, that's in the language, AB, AB, in the language, AB, 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 in the language. But these things down here, not in the language. AC, not in the language because the letter C right here, not contained anywhere in this regular expression. BA, not in the language because AB is in the wrong order. BABA, not in the language because even though AB is contained in here once, we have these other extraneous letters down here that are not contained in the language. And I'll run this real quick by just copying and pasting. So define regex like that. I guess actually I need to also do the import RE. And this pattern, compile regex like that. And then if we do a match, anytime that the string actually matches the regular expression, this is the string, this is the regular expression. The regular expression, again, is what defines the language. This is something that we are testing, whether it is contained in the language or not contained in the language. AB right here. Anytime we get something that is in fact in the language, Python will output this, what's called a match object in Python. But anytime we have something that is not in the language, like AC right here, then we get none as output, which the Python interpreter just doesn't display anything. So this is sort of like one of the prototypical examples of a regular language. Just have two characters that are repeated over and over again. Any questions about this language here so far, or the regular expressions? Is this mostly familiar to people? See, handful of head nods. Okay. So more generally, languages can be represented by what's called a grammar. And I've got a bunch of definitions up here. Grammar is a set of what are called production rules. Down here in this string right here, the production rule is this entire line right here. Anytime there's a colon in the string, that's a production rule. This thing to the left of the colon is the name of the production rule. And this thing to the right of the colon is what the rule does, the body of the production rule. And these grammars are used for generating strings in a language. There are a handful of synonyms that you'll hear for this word grammar, Bacchus-Naur form or BNF, or extended Bacchus-Naur form, EBNF. You'll see both of these used in, say, like the llama.cpp or whisper.cpp documentation. And those are, again, just exactly synonyms for the word grammar by itself. The language up above, which is called AB+, just named by its regular expression, can be defined by this grammar down here. And what this grammar says is it's a recursive grammar where our start rule right here, the string can contain either AB all by itself, or it's AB appended to the rule start right here, or prepended to the rule start. So this, again, is recursive. So if we have just this string right here, the way this string will match is that it'll apply the rule start here, see that AB exactly equals this, and so this is in the language. When we have the string AB right here, and we have this production rule start, it will first check AB right here. See that AB is not exactly equal to all this, and so it can't take this left-hand side of the OR right here. This vertical bar behaves the exact same way in regular expressions as it does in grammars. It's called the alternation operator. It means or. It means that this rule does this thing on the left or this thing on the right. And so this language right here does not match AB right here. And so it does not choose this left-hand side. It chooses this right-hand side. Consumes, we use the verb consumes the first AB token right here, and then applies recursively this grammar again, this rule again. Start, we've already consumed this first AB token by this right here. And then the second recursive call AB right here will consume the next AB token like that. And so that's why this recursive rule matches this, or this string right here is contained inside the language defined by this grammar right here. The same things as above. This not contained in the language because it contains the letter C. Not contained in the language because it's BA instead of AB. Not contained in the language because even though it has an AB in the inside of it, the very first two strings, BA right here, are not going to match either of these two strings right here. I'll copy this inside of Python so we can see what this is actually going to do. Lark not defined, I have to import Lark. Again, Lark not built into Python, so something that you have to pip install like that. And then if you do in fact, if the string is in fact in the language, you'll get an output that looks something like this. And if the string is not in fact in the language, then you will get a big giant error like this barfed out of you. The big picture first takeaway here is that regular languages, again, correspond to regular expressions, and regular expressions can, or regular languages can be written by a regular expression, or they can be written by a grammar like this. We will see in the next example, though, that grammars are more powerful than just regular expressions. Any questions on this example? Yeah.
So the you call that alternative or production? Or not, I guess it's not production, like the left AB, yeah, the left part.
So the technical terminology here is that this is called an alternation operator. The thing to the left of the alternation is the AB token. The thing to the right of the alternation is the AB token followed by the start recursive rule.
And then the left is AB. What is will consume something significant? Because it's recursive.
Correct. So the AB token here, the only way that this will match is if it's the AB string all by itself. And for example, ABC right here, this AB does not match because of that extra C down here. And so when I ran this, we get this unexpected characters exception because there is a C that is the unexpected character, and it's not found anywhere here, not ABC right here. That answer your question?
Yeah.
Cool. Good question. Other questions so far about the grammar right here? Okay, let's see. One thing that is very tempting to do is to talk about, and I've tried to avoid this in my language so far, but try to talk about like what this grammar does using verbs that imply action somehow. These grammars are declarative, not imperative. And so this grammar doesn't define how the parser, Lark here is called the parser. This function right here also called the parser. The parser is the thing that takes the grammar or takes the string and checks whether it complies to the grammar or not. These grammars are declarative, defines like what a valid language is, but not how to check whether a language is valid or not. And it turns out there are many different algorithms with many different runtimes in different situations about how to verify these grammars, how to check these grammars, how to parse these grammars. So try not to think about like step-by-step procedurally what's going on here, and think more declaratively about like just what's valid versus not valid. Okay, so this is the first like interesting grammar that we're going to see down here. And so my note up here says grammars can be used to represent languages that are not regular. And this language right here is not regular. It is what's called a context-free language. So let's take a look down here at the examples of the language. And it seems closely related to our previous language. This term AB right here is in both languages, both this language right here and the regular language above it. But this term right here is not contained in the regular language above. This language is called A to the N, B to the N, because the only strings that are contained in this language are strings that contain exactly the same number of A's and B's immediately after each other. So 2 A's exactly followed by 2 B's contained in the language, 4 A's exactly followed by 4 B's contained in the language, 4 A's followed by 3 B's not contained in the language, 4 A's, 4 B's, that part's good, but there we have this extra C here in the middle, not contained in the language. This is one of the prototypical examples of something that can be done with context-free grammars, but cannot be done with regular expressions. Here, the grammar, the first thing that jumps out to me about the difference between this grammar right here and our grammar up above is our grammar up above, when we have a recursion, we have a recursion with, again, this is called a term right here, with only one term on one side of the recursion. Down here, when we have a recursion, we have 2 terms right here, an A and a B, and they're on both sides of the recursive part right here. When this happens, this is what makes something not regular. When you have a recursive expression where there are terms on both sides of the recursion, this is what makes something not regular. And so how this is going to be parsed is that this language right here, we have the A and the B. The A and the B right here just matches the left-hand side exactly as before. And so this is in the language. More complicated right here, though, is the ABB string right here. When we see this string, this is not going to match. And so it can't choose the left-hand term of the alternation here, has to go onto the right-hand side here. And in this recursion right here, the left-hand A, that's going to match the very beginning of our string down here. And the right-hand side B over here, that's going to match the very end of our string over here. So this A right here matches this A. This B over here matches this B. And then the start will get the things in the middle right here, AB. And so then recursively applying the grammar, trying to match the AB, we'll see that we can in fact match the AB with this right here. So again, yeah, if it's at the left-hand side, starting from the beginning of the string, if it's at the right-hand side, from the end of the string. And then whatever the recursive part here is gets sort of absorbed in the middle. Any questions about this first context-free grammar here? Yeah, I mean, question is why, if it's on the right, we go to the end of the string over here? And the answer is that's just what it does. That's the definition of how these grammars work, is that whatever string we're trying to parse, again, parse is the verb for applying a grammar to a string to see if the string satisfies the language defined by the grammar. Whenever we have a string that we're trying to parse, if we have 2 terms like this, then the A over here is going to be lined up with the left-hand side over here, and the B over here lined up with the right-hand side. And the thing in the middle is where the recursion will happen. Did that answer the question? This ability to have things on both sides is of our recursion is what lets us have like some sort of counting operation going on, which lets us, in this case, make sure that we have the exact same number of B's that will happen after the number of A's. Other questions on this grammar so far? Okay, the next interesting grammar, this is the prototypical example of a context-free language down here, is called the deep language. There are many things in theoretical computer science that have unfortunate names for English speakers that I've heard a lot of people call this the Dick language or the Dyke language. But this one is conveniently for us a Dutch word, and it is actually supposed to be pronounced as the Deek language, which has no unfortunate connotations. The grammar down here is very similar to our grammar up above, but we've replaced the A's with the left-hand parentheses and the B's with the right-hand parentheses. The only thing that's different is I have a plus over here in my recursive definition right here. This plus corresponds to the same plus in regular expressions. It means the thing in the middle right here can be repeated one or more times. So this language is the language of all balanced parentheses. All of these have balanced parentheses wherever there's an opening parenthesis, there is a corresponding closing parenthesis. This language or this string right here not contained in the language because there is no closing parenthesis for the opening parenthesis. This string right here not in the language because we have an extra closing parenthesis with no associated opening parenthesis. So this is the language A to the N, B to the N, and this deep language right here. Those two together are the standard examples of context-free languages that cannot be done with regular expressions. Any questions about this language, Ben?
So the first parenthesis is continues directly to start, but there's another clause and the right parenthesis. So why does no a clause in front of the start?
Question is, this plus here, why is it after the start and why is there no plus before the start?
Yeah.
Good question. So this plus here, the plus is from the regular expression syntax, and it means repeat the recursion, repeat whatever the expression is to the left-hand side one or more times. In this case, it happens to be a recursion, but it doesn't have to be a recursion. It's just whatever happens to be to the left-hand side. So plus means repeat the left term one or more times.
Is it the one or zero?
Star means repeat the left term 0 or more times. It's the more theoretical explanations of regular expressions or grammars only talk about star because if you have star, plus is easy to implement from star. But in practice, it's useful to have both of these. But so the plus means exactly one or more times. In this case, we could replace the plus with a star and it would define the same grammar, but something weird would happen, which we're not ready to talk about. The actual question, though, was the plus here, what would happen if there was a plus before the start, something like this. And what this plus right here means, so this is still a valid language. It defines a language, but it is not a deep language. It is not a language of balanced parentheses. What this plus right here is doing is it's saying that this left-hand open parenthesis can be applied many, many times. before doing the recursion. And so with this plus right here, it's okay to have 2 open parentheses before a closed parenthesis. And so with this plus right here, something like this would be in the language. So this plus is intended to be applying only to this start recursive term right here. That answer your question, Dan? Or? Okay. Yeah, so again, I'm speed running the 2 semesters of stuff right here. So I'm trying to go a little bit quickly. It's okay if the full details about things are a little bit fuzzy, especially at this point. The next set of examples will make things, I think, a lot more clear. I'm going to pause, though, the Python stuff right here and take us back over to looking at the whisper.cpp grammars. Let's take a look at the chess grammar. And here's the grammar for chess. And we'll just see there's some slight differences between the syntax that whisper.cpp expects and the syntax of Lark, but the big picture ideas are all the same. So in whisper.cpp, when we have this : equals, that's the same as just a colon in Lark. So this is a single command or a single rule right here. The left-hand side root is the name of the rule, and then the right-hand side over here are the options of what you're allowed to do. We'll see some more examples next time of where we have multiple recursions going on. So this has 4 different recursions happening inside of this rule right here. And these recursions are not back to root. They're to different rules being called. So init right here, go into that, move coming down here, and yeah, big long expression right here. Everything else, though, is only regular expression syntax. So here, the A to H in square brackets, this means that any letter A, B, C, D, E, F, G, H, 1 to 8, any number 1 to 8. The question mark here means that the thing to the left-hand side happens either 0 or 1 times. So this move right here, what it's saying is that we can have a piece or a pawn or a king. Piece, king, pawn defined like this. So the piece can be bishop, rook, knight, or queen. Any of those things can be substituted right here. Pawn has to be the exact string pawn. King has to be the exact string king. So any of these things right here, any of the valid chess pieces can appear right here in a move. And then we'll have a space followed by 2 with that's optional. So you can say king 2, A1, or you don't have to say king 2, A1. You can just say king A1. And this thing is optional because it has a question mark after it. And you also don't even need to specify the actual piece name right here with this question mark. The name of the piece is optional when you're giving commands in chess. If you don't specify a piece name, it defaults to being a pawn, and you can just specify the square that you're moving it to. Yeah, it'll take some, I don't know, thinking about things to make full sense of these grammars, but once you get the practice of it, it's not too bad. So that was chess. Let's take a look at the assistant one as well. The assistant one here is the one that you'll actually have to modify. And the modification should be fairly straightforward. You're just adding a new command into this rule right here. So here's all the different commands that you can give it. You'll be adding a new command of kill all. So instead of saying like hide device, it will be kill all inside of strings right here, and then the options that you're allowed to kill. You'll have to define a new rule down here for the things that you're allowed to kill, which I think I said are humans or robots or animals. And you add that rule right here, and then Whisper will recognize that those things have been said. I don't know. Any questions about the syntax here, how it's different from Lark, or what needs to happen for the homework? There are a lot of weird things that go on in these grammars, and parsing these grammars can be very complicated, and writing these grammars can be very complicated. Again, we'll see more of those examples in subsequent classes, and what about that makes them complicated. But the stuff that you have to modify here for assistant should be relatively straightforward and not get you into weird, hairy edge cases. I guess that seems like a good spot for us to end a couple minutes early today. If people do have questions, happy to stick around and chat about those questions after class here. Otherwise, have a good week. See you guys on Wednesday.